The Doppler effect is something that you have experienced many times. When a car drives past you, you experience the Doppler effect. That sound is evidence of the Doppler effect. Now we can use the same ideas when we are discussing stars to determine if a star is either moving towards us or away from us. We are first going to discuss how the Doppler effect works with sound and then relate what we know back to stars. So here we go. Now imagine a fire truck, police car, or ambulance is driving towards you. What do you notice about the sound coming from the fire truck? Well, the sound should get louder, obviously, but that's not what the Doppler effect is. Think about it. Doesn't the pitch or the note the sound is making getting higher as well when that fire truck is moving towards you? Well, the reason why the sound seems to be turning into a higher note is because the sound waves out in front of the fire truck are actually being compressed a little bit. Now remember, the shorter the wavelength, the higher the frequency. When we're talking about sound waves, higher frequency equals a higher note. Let's think about this though. What if you were the fire person driving the fire truck? Would the note sound like it was getting higher or lower just sitting in the truck? Well, since you're moving with the fire truck, and the note should always be the same. People outside of the truck only hear the change in the note because of the motion of the source of the sound waves. Now on the flip side of things, once the fire truck passes you, the sound waves are kind of stretched out a little bit. The wavelength increases, making the frequency lower. And just as we discussed with sound, as frequency changes, so does the note that we hear. In this case, the note would sound lower due to the longer wavelength. Now in your notes, you have the exact same picture, this one right here, as you see on the screen. I want you guys to draw circles around the police car. So draw like 4 different circles around the police car. That represent the sound waves it is producing as it drives towards the little boy over here. Here's my arrow from right to left. I also want you guys to label where the long and short wavelengths would be, as well as where the high and low frequencies would be. So take some time to pause this video to do that. Once you think you have it, play the video to check. Alright. So your circles should look like what I've got here. Okay, these circles of sound waves should be closer together on the left-hand side of the police car and then further apart over here on the right-hand side. Now since the waves are closer, they should have a shorter wavelength and a higher frequency. So this little guy right here would be starting to hear a higher and higher note. Whereas the longer wavelengths and lower frequency are over here. This little girl is going to be hearing a lower note. Okay, so we're going to be switching topics a little bit and discuss light and the Doppler effect. There in your notes, there's a couple questions at the very bottom. Make sure you answer those. So pause the video, answer those first before you go on. Okay, so it's easy to understand how the Doppler effect works with sound because we can hear it all the time. Now with stars, we have to deal with light because that's the only thing we get from them. The tricky question is, how do we actually see the Doppler effect? Well, since light also travels in waves, those waves can also be compressed or stretched out depending on if the star is either moving towards us or away from us. Now if the star is moving towards us, the light waves would be compressed, making the wavelength shorter. Okay, let's stop for a second and think about this. What color, from red all the way to violet, has the shortest wavelength? Well, hopefully you remember that it's this violet over here on the right-hand side. Now, what astronomers see when they look at spectra for stars that are moving towards us is that all of these little spectral lines, these black ones, actually shift towards the blue end of the spectrum. And because of this, we call that a blue shift. Now, here's the tricky part. We have to use a star that is not either moving towards us or away from us. Luckily, we have the sun. So for example, this top spectrograph, or spectrogram would be for our sun. This one down here at the bottom would be for some other star in the universe that we're trying to figure out if it's either moving towards us or away from us. What we can do is we can take a look at a spectral line like this one in our sun and compare it to a spectral line in this other star. What we notice is if we go straight down, oh, it shifted. And in this case it moved over towards the blue side. Okay, same thing, we can take a look at this one right here. Go all the way down, oh, it shifted again over to the right. Okay, in this case, that would be a blue shift, and we would know that this star down here would be moving towards us. So using what we already know about the Doppler effect, we should know that if a star is moving away from us, the wavelength of that light should also get longer. Now the longest color wavelength is red over here on the left-hand side. So stars that are moving away from us are called red shifting stars, or they're red shifted. Okay. Again, we have to use our sun because it's not moving towards or away from us. Compare it to other stars in the galaxies, in the universe. And what we can see is, we'll take this guy right here all the way down to the bottom. This one actually moves over to the left, over towards the red. This one right here, go all the way down to the bottom. That one moved over to the left. So that would be red shifted. And we would know that this star now is moving away from us. Well, that's it on the Doppler effect. Watch this video as much as you need. Thanks, guys.